Welcome to the Puro Earth webinar on enhanced rock weathering. Let's give people 1 minute to join and then we can start. So it is 1 minute past the hour. Let's get started. Welcome everybody to this Puro Earth webinar on enhanced rock weathering. I am your moderator today. My name is Marianne Tikkanen. I'm the head of science head of standard in Puro Earth. And you will hear today from two of my colleagues, Dr. Sebastian Haas from the science team and head of science, Dr. Richard Haas.
Hello.
And we are targeting to be ready in about 40 minutes, starting with the presentation of the revised enhanced rock weathering methodology, and then leaving good time in the end for questions and answers. Next slide, please. So for questions and answers, please use the Zoom function for Q&A at the bottom of your Zoom window, and you can put in your questions during the presentation, and we will then pick them up after the presentation. And this webinar is being recorded, and the recording will be published afterwards. And this is your time to influence. So the team has worked hard on revising this methodology, and now you can give your comments and do use the links to give the comments. Next slide, please. These are the methodologies currently available under the Puro standard. The top row is the ocean methodologies, and the bottom row is the land-based methodologies. This year we have very heavily focused on the ocean-based methodologies and at the same time revised the land-based methodologies, where this enhanced rock weathering is one of those, and it has now gone through a major revision, meaning that all the newest scientific advances have been considered and included. But with that, I think I hand over to you, Sebastian, to go through the key things in the presentation.
Yes, thank you, Marianne. And one more chance here to scan this QR code to directly get to the blog post for the enhanced rock weathering update, and that will also lead you to where you can give feedback. All right, let's dive into enhanced rock weathering, starting with an introduction overview. So here I want to give an overview of what we're talking about when we talk about enhanced rock weathering, which I'll also be using the acronym ERW for throughout this presentation. So broadly speaking, we're talking about spreading eligible feedstock onto soil, usually agricultural fields. Eligible feedstock usually is natural rocks, but it can also be similar substances such as slags, mine tailings, recycled concrete, or cement kiln dust. For practical purposes, it's quite important. So yeah, for practical purposes, quite important for it to be capable of undergoing carbonic acid weathering, which is the goal of enhanced rock weathering. And then, of course, eligible feedstock also needs to be environmentally safe. We'll get to that later. But yeah, to the weathering, to the core of the technology, basically, we have here an example of weathering of an exemplified silicate mineral that reacts with, in this equation, CO2, but really carbonic acid, to create bicarbonate anions as well as cations, so positively charged ions like calcium and magnesium, which we also see down here in the sketch. So this is the core reaction of enhanced rock weathering, creating out of atmospheric CO2 these bicarbonate anions, which can then be transported out of the soil into the groundwater via rivers to the ocean, which constitutes the ultimate storage site for atmospheric carbon under this technology. For this to happen, I omitted two steps prior to feedstock application. So we also need transportation of the feedstock material or weathering material to the field. And that feedstock also needs to be sourced somehow. So for example, in a mine for natural rocks. All right, so enhanced rock weathering can be a safe and durable carbon storage technology, which can even have co-benefits. So the durable storage derives from this type of storage. So it's bicarbonate in the ocean, which has a residence time there of thousands of years. So this methodology has the stamp of 1,000 plus years durability. It's safe, provided for people and environment, provided responsible environmental monitoring and safeguards, which is, of course, one of the tasks of our methodology to provide the framework for this kind of safety. The core benefits that I mentioned include improved soil health and fertility, as well as the fact that usually no additional land use or land use change is necessary because existing agricultural land can be used for this technology. A challenge for ERW has been effective MRV because it's challenging because of the inherent variability and complexity that we're dealing with in these semi-natural systems of agricultural fields, as well as the slow weathering kinetics that we usually look at when you look at rock weathering. That can be challenging for the existing quantification methods to pick up on a signal of this weathering. So that's one challenge that we're trying to address in this methodology to provide the guidelines for effective MRV. So here I want to give an overview of the main differences between the previous Puro Earth ERW methodology edition 2022 and the new updated one that will be published later this year. I'll go into all of these points that will appear on the slide later on in the presentation. Just want to give you an overview, starting with the enhanced quantification approaches. So we're able to describe 6 different eligible CDR measurement approaches in this methodology, partially thanks to just like the scientific progress that's been ongoing over the past 3 years here. That allows us to be more precise in the description of these evolving methods. Another aspect that I want to flag here is that we are going to require the combination of 2 of these approaches now, which is also new. There's also detailed sampling requirements that are meant to improve the rigorousness and statistical representativeness of the measurements. The role of modeling is clarified. We'll get to that. The accounting for loss terms is updated. There's another case where also scientific progress has enabled us to improve upon what was in the previous edition. And one large new chapter and elaborate new chapter is the one on uncertainty, where we are introducing an uncertainty discount and generally speaking, a robust quantification of uncertainty and propagation. Let's start with environmental safety and life cycle analysis. So in the environmental safety chapter, the focus of it is on this list, basically, which the first three constitute potentially toxic element, PTEs. First and foremost, potentially the heavy metals, but also including asbestos and radionuclides that need to be tested in feedstock, and for the heavy metals also in the soil as an environmental safety measure. A fourth point here is somewhat a different category where also the respiratory risk from rock dust inhalation, for example, for workers or just maybe neighbors that can be exposed to that needs to be taken into account and in all cases minimized, mitigated, and monitored. So in terms of environmental safety, the key changes in addition and additions in this updated edition are some clarifications around potentially toxic element thresholds that now default to local regulations. There has been more of an emphasis on soil organic carbon, where we require monitoring now. This has also been an active area of recent research in terms of understanding the influence of ERW on soil organic carbon budgets. So we're requiring the monitoring and recommending countermeasures if sustained soil organic carbon reduction is observed. Another thing to say about soil organic carbon is that if it's lost due to land use change, if there is land use change, then this loss would also be accounted for in our embodied emission accounting scheme. And that leads us to the life cycle analysis part of the methodology, where in these three project stages, so sourcing of feedstock, transport of feedstock, and application of feedstock, we require the accounting for operational emissions that are part of the process. What's lacking here is the stage of weathering, actually. And that is on purpose, of course, because during the weathering stage, the main activity would be monitoring, and we don't want to discourage monitoring from by requiring operational emission accounting during this phase. So in Puro Earth lingo, so to speak, accrediting period is a 5-year period for which a production facility gets accredited. During these 5 years, you can have several deployment periods, here DP, which would start every time fresh feedstock is applied to field. Each of these deployment periods can be further subdivided into monitoring periods, where the carbon dioxide removal supplier would decide the end of a monitoring period by taking one more measurement, a final measurement for CDR quantification. And if then there can be, based on these measurements, evidence presented for net carbon dioxide removal, this could be credited. And the point I want to make here is that project emissions can be amortized evenly across these deployment periods and subtracted from core calculation during each monitoring period. With that, we move to the big topic of CDR quantification. So CDR quantification at Puro revolves around the Cork equation, which for enhanced rock weathering looks like this. So it starts with C stored, basically the gross CDR measured as weathering signal on application sites in the field. What's subtracted from that is, first of all, the baseline, which I'll get back to in a minute. It's measured on control sites. Then loss terms, which I will have a slide later on to get into details around that. And the project emissions that we just dealt with on the previous LCA slide, and any economic leakage terms. So for the baseline term in the Cork equation for ERW, it has two components. The first one is the in-field component, which can be addressed by control plots, or is addressed in this methodology by control plots. So here we're talking about weathering that would have occurred anyways in the field, even without the ERW intervention. And that can be controlled with by control plots to which no feedstock is applied. That is the field component of C baseline, and then there's a feedstock component of C baseline, which deals with counterfactual feedstock weathering. Which an example of that would be, or the meaning of that is that the feedstock that you bring out in the field in ERW. If you did not take that to spread that out on the field, maybe it would weather to some extent anyways, perhaps sitting on a pile in a mine somewhere, and that needs to be assessed as well. We expect that to be usually a small term that needs to be assessed to an extent to account conservatively for such counterfactual feedstock weathering. Okay, so when we talk about quantification of C stored and also basically C baseline and C loss, many of the C loss terms, as we'll see, are quantified by measurements. The first practical thing we think about is sampling. And there are many different aspects and dimensions to sampling that we had to sort of get our head around and consider during the methodology development. And I want to list a few of these here to give you an idea of what this is about. So the first aspect dimension is the vertical dimension of sampling depth, and for that we incorporated the now fairly common near field zone, far field zone concept that potentially was introduced by the Cascade Foundation in 2023. At least that's where I first encountered it, which is a useful concept that defines the near field zone conceptually as the upper part of the soil layer in the field of a ERW production facility, and that in that upper soil layer, it's also defined as the part of the soil where most of our enhanced weathering will occur. So this is what we're interested in when measuring enhanced rock weathering activity. So that meant to us that the bottom of the near field zone should also be the sampling depth that we're recommending to sample to take soil cores to that depth, or to take water samples at that depth. And so the sampling depth in our methodology is defined conceptually as the bottom of the near field zone, and practically as usually 20 centimeters deep. Because as useful as the concept of the near field zone is, it is also difficult to actually, generally speaking, say how deep that is, and 20 centimeters seems like a good practical depth to use for that. And so I haven't talked about the far field zone yet. Far field zone is then everything sort of below and downstream of the near field zone, and that's where the weathering reaction products would go, and so that would include the deeper soil layers, groundwater, rivers, and the ocean. Another quite different aspect of sampling is sampling density. So how much do you sample per hectare? That was another difficult one for us to find a good generic solution to. Which we settled on was to require what we think of as absolute minima. That ended up starting at 3 soil samples per hectare and 1 water sample per hectare. And then actually we applied a square root decay function to slightly decrease the samples per hectare as you increase the hectare in your field. But then of course the absolute number goes up, but the relative number of samples per hectare goes down. And again, we're thinking of these as absolute minima, and we expect that the setup of this methodology will actually incentivize a higher sampling density because of the uncertainty discount, which we'll later talk about, which very briefly basically means the lower your uncertainty around your corks, the more corks you can get. And that incentivizes decrease of uncertainty, and the more you sample, based on the law of large numbers, the more your uncertainty should decrease. So that's sampling density. And sampling strategy is potentially a bit of a vague term. What do you think about as sampling strategy is like, where do you actually sample? How do you decide which places you actually sample? And in that context, we first require a pretty thorough pre-application soil analysis to inform on the understanding of the supplier's understanding of the field site. And then based on that, the methodology requires that you subdivide or stratify the production facility into strata, indicated here by these colored areas. And these strata sort of similar soil characteristics based on this pre-application soil analysis. And then the idea based on that is that control sites indicated as C within these homogeneous strata can then be considered representative of the rest of the stratum. And they can sort of be compared to the rest, to which feedstock is applied to undergo sort of these calculations in the Cork equation at the end of the day. And one more word about control plots, because they feature very large in this methodology. They really account for this field component, which is the major component of the C baseline term. So they're subtracted from C stored, and they are really the business as usual case. So they also correct ideally for the liming counterfactual, for example. If there was agricultural liming done before ERW started in a given place, then the control sites ideally should be limed as well to account for this business as usual case. And so when we're done with sampling, the next step is analyzing the samples. And so we're outlining 6 different approaches for C-stored quantification with these 6 approaches listed in this table. We describe each of these approaches in detail, including equations that can be used sort of as a template to quantify or to calculate C stored and C baseline on the basis of data coming out of these different approaches. Another thing we require here is the combination of 2 approaches. And one needs to be a soil sample-based approach, like the 2 top ones here. And the other one needs to be a soil water-based approach, like 3 ones down here. And one of them needs to be assigned as a quantification approach. So as the name suggests, quantify the C stored. And then the second one would be assigned the validation approach that would validate the quantification approach by yielding results that are in the statistical ballpark of the quantification approach. Okay, so what's the role of models in all of this? You may have gotten the idea that in fact this methodology is very much focused on quantifying C store through measurements, which is correct. Models can still have a role. It's an optional role to the supplier. They may use it to extrapolate field measurements, and that would be incentivized by the reduction of cost and effort from sampling. So they can reduce their sampling effort, basically, by applying models, which would be encouraged. In order for models to be fit for quantifying C stored, they must meet a range of minimum standards that includes, but is not limited to, being based on models that are described in peer-reviewed papers, being process-based, simulating a relevant set of physical and biological phenomena. They must output expected weathering and associated CDR over time, and they must be validated against site-specific empirical data. And if you're into ERW models, here's a few examples of model types that would be eligible in principle, like the soil model for enhanced weathering, SMOO, a coupled ecohydrology biogeochemistry model by Bertani et al., or various 1D reactive transport models like the SEPTA model presented by Kansaki et al. 2024, or Freaksy-based ones like the one by Kelland et al. 2020. Getting to the loss term in the Cork equation, losses can occur in the near field zone and in the far field zone. They need to be quantified if they are applicable by measurements, modeling, or conservative estimate. So the near field zone losses that are dealt with in this methodology are non-carbonic acid weathering, plant uptake, cation adsorption, secondary carbonate precipitation, and secondary silicate precipitation. The latter is a bit of an exception because there's no quantification approach that is scientifically feasible currently. So approaches that implicitly correct for this particular loss term are encouraged. The other losses all have descriptions and protocols for how to account for them using measurements or models in the near field zone. So for example, the non-carbonic acid weathering loss can be estimated by measuring anions and estimating the export from the near field zone, or alternatively with a model modeling the carbonate system. And I won't go into the other examples. You can read those in the methodology. Briefly on the far field zone losses, there's two loss terms here. The losses from surface freshwater systems, mostly thinking of rivers here, and losses from marine systems. With the rule for the river losses has become fairly elaborate, where we require a small amount of monitoring from nearby rivers if the data don't already exist in databases, for especially pH and the saturation index for calcite to monitor for the risk of carbonate mineral precipitation or carbonate system shifts resulting in CO2 outgassing potentially. And so then based on this risk assessed by this monitoring, we would require different stages of modeling these losses or different types of conservative estimate based on these risks. The marine system loss is slightly less complex, but also gives options to either estimate the loss yourself if you're a supplier, or take a conservative estimate based on scientific literature. Okay, so last topic before I close is on uncertainty. So as I said, this is a big chapter we added compared to the previous edition, where we now require specifically the quantification of uncertainty in each of these cork terms. There's a bit of an asterisk to the each term part of this that I'll get to in a few seconds. So quantification by Bayesian of frequentist approaches of the different terms is the first step. Then this uncertainty would be propagated across the different terms to arrive at an overall uncertainty for the corks that is calculated. And then here's my asterisk. So not each of these terms shall be quantified. Some of them are optional. These include the uncertainty around leakage, the uncertainty around the loss term, and the uncertainty about the feedstock component of the baseline term. So not the field component. The field component the uncertainty needs to be quantified. But for these three, it's optional. And the rationale behind that is that these are already sort of conservative estimates or conservative considerations subtracted from the corks that we don't want to further sort of penalize with the associated uncertainty discount that we get to next. And yeah, so this is the uncertainty discount. So then potentially disregarding these three terms, you would have your cork uncertainty that would have to be subtracted here in this equation from the 100% corks that you get from the actual cork equation. So let's say your uncertainty is 10%, you would arrive at 90% as a value for this factor, and then quite straightforwardly this would be multiplied into the cork equation, and so you would only get 90% of the corks that were calculated without the uncertainty consideration. And so why do we implement this? What's the motivation behind the uncertainty discount? So we think that the nature of ERW quantification is possibly a bit more uncertain than other CDR technologies. And so we want to encourage basically the market or the public to have trust in the outcome of CDR quantification in ERW through this methodology, and to really have trust that one cork equals 1 ton of CO2 removed. And so we're following sort of the attention to this issue of uncertainty discount within the ERW field, as you can see in the Cascade Foundations document, and also beyond ERW, as you can see in the EU CRCF frameworks that deal with that. So following general market expectation and trying to improve the trust in the outcome of ERW, MRV, and CDR quantification here. And with that, I thank you for listening, and we get into the Q&A section where I'll also include my colleague Richard.
Thank you, Sebastian. And very good. We have good time for questions, so use the Q&A section. You can still put in your questions there, and I can then maybe combine some questions if we don't have time to cover all of them. I noted that I said that we have land-based and ocean-based methodologies. This seems to be in between because over a long time it will actually end up in the ocean. So this is kind of both land and ocean-based, as I understood. But then let's go to the questions. And you covered losses, many types. Was it 6, 7 types of losses there? Very well. There's a question about what is the biggest loss contributor? So their relative share compared to the losses.
I can answer that. So indeed, there are 7 different kinds of losses in the methodology, 5 in the near field zone and 2 in the far field zone. And now usually I would say that perhaps the biggest loss term would result from the far field zone losses, so the losses from the ocean and the surface water systems. Now that comes with a bit of an asterisk, as the situation might be variable due to sort of site-specific considerations. For example, in a field that has been, let's say, aggressively fertilized, there might be a lot of strong acids in the soil, which would contribute to weathering significantly, and that might then be a bigger component. And then it should be worth noticing that the counterfactual weathering can also be a significant term, which is not here in this loss term per se, but that does need to be evaluated and discounted as the baseline term. So yeah, these terms, I think.
Okay, thank you, Richard. So losses and also the baseline weathering can be significant. Then comment about that there is quite a lot work added to the projects here. So what are the implications of that to cost and timeline of the projects?
Okay, that's a great question. So there is indeed a lot of things are a lot more rigorous and more detailed in the methodology. Now that doesn't sort of fully equate to an equal amount of added work, because many of these requirements are something that we have already required, but not in let's say so many words. So many of the requirements are actually adding detail on the principles that were already included in the current methodology. And now it's true that it's likely that there is going to be some increase in cost, especially like monitoring costs or site management costs, because there is additional requirements around these. But I don't think that there should be kind of like a radical difference. And we should sort of note here additionally that there are a lot of other costs associated with ERW, like sourcing and transporting large quantities of rock, and these would essentially remain the same. So overall, I would say that if there is an increase in cost, it would be very moderate. But at the same time, I think that the added robustness of this new methodology, and also an increase in the crediting period length, which has an effect on project timelines, will enable sort of better scaling and increase stability in this market. So I think these benefits will far outweigh the sort of potential increase in monitoring costs, for example.
Okay, thank you, Richard.
And just to clarify, I believe I said 5-year crediting periods, which I believe was the previous length of crediting period, and now we've changed that to 10 years, right?
Yeah, thank you, Sebastian. There was a question about is the crediting period 5 or 10 years? So previous version is 5 years and the revised version is 10 years. Thank you for clarifying. Then next question about Cascade Foundation. You referred a couple of times to that. How much is this aligned, this revision of the methodology aligned with the Cascade Foundations?
Well, we've been paying close attention for sure to the Cascade Foundation document, and we in fact refer to that document many times in the methodology, and we've been in contact with Cascade, and they have been contributing to the methodology as part of the working group. And I would say that we've done an overall good job in aligning with the Cascade Foundation documents, and of course with other market standards and expectations as well. At times, of course, we have had to add operational detail, for example, to some sections to ensure that these rules are then followed consistently across projects, and they are sort of operationalizable to the extent that we want them to be. Like for example, with the uncertainty quantification. So here we try to align with the Cascade Foundation recommendations on the sort of general methods of quantifying uncertainty and the sort of uncertainty threshold, like creating threshold for the discount, but we've added a lot of equations and other detail in that section to ensure that all the relevant terms are accounted for and in the sort of proper fashion that we want them to be.
Thank you, Richard. So aligned where it has been possible. Then a question about the limitations. Are there limitations in the methodology when it comes to geographies? Are some geographies not eligible for ERV projects?
Perhaps Sebastian, can you take this?
Sure. Yeah, so no, in principle, there's no like geographical constraints, like you can do it anywhere on the planet. One question is, does it make sense to do it anywhere? So there's certainly advantages to do it in warm and moist or rainy places, which would improve the weathering rate, generally thought to improve that. So there's practical reasons to choose different locales, but no constraints per se, other than that, like for one given production facility, that needs to be within one country, and that just has sort of advantages of dealing with only one jurisdiction. And we also require it to be broadly in the same climate zone. And that's, again, talking about one production facility where like one supplier could have various production facilities scattered around the world in theory. But like one production facility has to be within one country and one broader climate zone.
Thank you, Sebastian. We have maybe time for a couple of more questions. There is another limitation question about the feedstock. Can you take this as well? Are there limits to feedstock eligibility?
Yeah, basically, the limits on feedstock eligibility are environmental safety considerations. So they would have to meet the environmental safety tests. So tests would have to be done on the feedstock to test for potentially toxic elements, right? And if these thresholds, if they are considered safe based on regulatory thresholds, they would basically be allowed. And then also there would again be a practical consideration again, is it an effective feedstock? But that's not regulated by our methodology, so that would have to be sort of clearly just be an incentive for a supplier. And then other than that, it can be usually natural rock, but it can also be like I already mentioned, less natural materials like slags, cement, kiln dust, stuff like that. Yeah.
Okay, as long as they meet the safety requirements for the content of the mineral or material. Let's take one final question, and this is about the timing. When will this methodology go live, and how long can the previous methodology be used? Is that you, Richard?
Yeah, happy to answer that, Marianne. So the target for the launch, like final launch of this methodology would be in December this year, and we will provide a more detailed sort of transition plan to accompany the launch of the methodology. So, like very briefly, what happens between now and then is the public consultation period. Then we will do changes as a result in the methodology. After which it would go to our scientific advisory board for approval. And after the final version is approved, we can finalize all of the supporting document for this methodology, for example, the audit package documents. And then the launch would be in December. And in general, we've dealt with this such that facilities that have been registered before the launch date can still be audited against the previous methodology version for a transition period of a couple of months. This is for example what was done in the biochar methodology. So we will follow that course of action here as well, and we'll detail all of this in more detail, of course.
Okay, thank you. And maybe this is a good reminder for everybody about the ongoing public consultation. It's roughly 10 days left. The last day to give your input is 28th. And this QR code takes you to the page where you find the document. So the revised methodology draft with all of this content, and also a form to give your input in, so that it is easy for the team to address the comments and make the changes if that is needed. But then I think that we have come to the end of this webinar. Any final comments? How would you wrap up this, Richard?
Yeah, so thinking back, we released the first ERW methodology in the market about 3 years ago, and what a leap have we taken in learning. So we learned so much during these 3 years, and like as ERW itself takes time, we have also needed that time for learning, and we'll sort of continue to learn new things about ERW as more and more projects scale up. And I'm really proud of our whole team for pulling this off. But at the same time, we absolutely could not have managed this without all of the support and collaboration from project developers, academics, buyers, and all sort of participants in our working group, and all of the other stakeholders who have provided such invaluable feedback during the update, and it's really been sort of invaluable. So a huge thank you to all of those who have contributed to this update, and who will contribute by sending in public consultation comments for helping us to make this methodology the best that it can be. So thank you all.
Thank you, Richard. And Thank you all participants for listening, and we are looking forward to your comments to this methodology and seeing you in next Puro Earth webinars.